How's it going, everyone? Mr. Selector here to do a quick overview of our energy and work and power unit. So to start off, we have that work is force times distance, and when we're doing this, we're always making sure that's the displacement and the direction the force is applied. And then when this is over a period of time, or how fast the work is being done, this is referred to as power. So we have work divided by time, and this has energy of watts. So joules per second is going to be the units of watts for power. And then for the units of work, we have units of joules. So newtons times a meter will give you the units of joules. And then as you can see, we have the work energy theorem, which states that work is equal to the change in energy. So we have that boxed in right there. So work is the change in energy. And then we go into some of the labs that we have been doing over the past couple weeks. Now, the first lab we're looking at here is that force over the change in distance, and this gives us the slope of our line, which is our spring constant, and the spring constant is how difficult or how easy it is to stretch or compress a spring. So that's what that's giving us there. So newtons divided by the meter, so the force divided by the change in compression will give us our spring constant. Now looking at that, if we plug in force times the spring constant times the compression of the spring, we get that formula if we plug it into the area below that line, which will be the triangle, and we use that formula here. So that's just giving us the area of this triangle below, and we plug in the force at any compression distance multiplied by its spring constant, we get the energy for a spring. Now, this is one of the formulas that you can see up on the board in one of the pieces of paper, 1/2 kx squared. And this is one of the formulas you will be using on the test. Now, another lab that we did, we looked at the spring energy and kinetic energy over a certain period of velocity. Now, with that, we're looking at specifically how can we change this to be a perfect line like we are always looking for. And what we had to do was we had to multiply the velocity by velocity, so we get velocity squared. And when we plug that in, we get that the kinetic energy is 1/2 v squared. So the slope of the line is going to be 1/2 the mass, so we have that the energy of kinetic is 1/2 mv squared. And then finally we had energy over height, which is equal to the slope of the line, which is going to be our weight. And if we take our weight in basic form, we see that it's mass times gravity. So weight is force of gravity, and then we break it up into its components. So mass times the acceleration due to gravity, and multiply it by its height. So that's how we got our potential gravitational energy. So those are the three energy formulas that we will be using. We have that the spring energy, or potential energy in a spring, is 1/2 kx squared. The k is the spring constant, so that's going to be the slope of this line, force times delta x. And then we have the kinetic energy, which is 1/2 mv squared. And finally we have gravitational potential energy, which is mgh. So those are our three energy formulas. Now these can be applied to the formula of total mechanical energy. So it states that the total energy before will equal the total energy after. And when we do this, we have that the potential energy of gravity plus the kinetic energy plus the potential energy in the spring is equal to the energy of gravity plus the kinetic energy plus the potential energy of the spring after. And depending on the question being asked, we'll get rid of the variables that we don't need If the object isn't moving, we won't have kinetic. If it's not compressing a spring or doing anything along the lines of elastic motion, we will not use the potential elastic energy. And then when we get rid of all of the variables that we don't need, such as the scenario seen below, we have a ball being dropped off a building. It starts out with gravitational energy and it's converted into kinetic energy. So we can just cross out kinetic and spring energy before, and we can cross out gravitational and the spring energy after. So we get that the gravity is equal to the kinetic energy. And then when we break it into its components, we have mgh is equal to 1/2 mv squared. Now this isn't going to be the case for every single possible scenario that we could ask, but using these steps, you'll get the formula that you need to solve the equation. So just look at the total mechanical energy, look at the 3 energies that could be involved before and after, then decide which ones are before and after, set them equal to each other, and solve from there. So that looks like it's it. I hope this was helpful, and if you have any more questions, feel free to come in and ask. Have a great day, everyone.